She told me that, yeah, we waited like maybe 5 minutes.
I love Sharon. No, my mom told me she would never pay for my college ever again.
Yeah, at this point, she's just gonna like learn how to do it.
Okay, don't forget on Wednesday, a little extra credit. Okay, we're also going to have another extra credit opportunity November 8th. There will be a speaker at 5 o'clock. Let's figure out what I'm going to do yet.
Is it on, what day is that on?
I don't know.
8th, Thursday.
It's Thursday, the 8th?
Yeah.
Yeah, that makes sense.
Friday's
The first
not.
is Thursday. Okay.
I'm gonna wear my Victoria's Secret.
Hello.
How many points is the
Then I'm gonna wear my cat ears.
I don't know. That's why I said I have this.
I gotta weigh babysitter money versus points.
I'm not gonna work out.
Figure out which means more.
You know, there might be two things. We'll see. I'm trying to figure out what I want to do.
I got a lot of cat ears. I wear my cat ears.
Okay, how many chiral centers? Pick your answer. I went to 5. Most of 0.
Make it for it on Wednesday.
You just shut the door on Quenisha, Ozzy.
I did?
Yes.
That's what you get for being late. What you get for being late? What you get for being late?
Dang, cat.
It's 11:01. I started you Hurry, hurry, you got to pick.
All right.
You missed all the extra credit announcements. All right, we're going to want purple.
Have you never seen my brother rock out? Thank you.
What's that one sentence you showed on the
It's kind of racist.
Okay, 24. So there's 5 of you that did make a guess. Nothing else. Pick an answer because I'm going to push the button. We all up there? I only got 23. I really want you all to have a try.
Answers on
The answer is what? Okay.
With your baby bump?
All right. I hope it's C. All right. So where do you think the chiral centers are? Is this a chiral center?
No.
Yes. Yes.
I just skipped that one. Is this one chiral? Nobody picked that? All right, now I want you to tell me, what is the absolute configuration for the chiral center below? You can do it. Did anybody bring their little girl?
We're too poor for that. We gotta use marshmallows.
That's all right. You could munch during class. I won't. gonna have treats on Wednesday.
Is that I or CL?
Is what now?
The I or CL?
Oh, it's ClCH2. Yeah, it doesn't make sense to be an I, because you don't have.
It didn't.
Okay.
I just wanted to be sure.
Yeah, that's one of the hard ones with fonts. That's why when I draw them, I go like that a lot.
Yeah.
Okay, we got 7 more to go, so let people think. And yes, you do have a 50-50, theoretically.
I voted for the first time. Never voted.
Well, I mean, yeah, you.
I couldn't vote. We can do it. I have that on.
Included all the models. Check those roles.
I'll go through and do it, so I'll do the whole shebang. Okay. So if you get it right or you get it wrong, you'll find out if you did it right. Okay, I got 23. Do I got one more? Nothing else, make a pick. Okay, so we're like, okay. Okay, so everybody found the chiral center. All right, just checking. Okay, so when you take one step out from this chiral center, you're going to compare C, C, O, and C. So what can you tell me right now? The O is 1. I guess purple's 1 today. Okay, then we're going to go out from that chiral center. So we had a C, and now what will we have over here? What are our choices going to be? A Cl and 2 H's. Everybody see how we get that? You're just taking a step out. It's like you're walking around the molecule. Okay, over here, we have a C, and then we have a C and 2 H's, yes. Okay, now, what do we do with the triple bond? We're here at this C that's purple, okay, and then what do we do? Swap and fill, so what will we have? 3C. See? Everybody see how we got those things? Okay, all right, now, what are you going to compare? Biggest guns. So who's number 2? The chlorine is number 2. Anybody want the chlorine to be number 1? You have to go stepwise. It's first point of difference. It's not my rule. You can yell at those other guys. All right, now who is 3? The 3 carbons, because you're going to have a carbon versus a hydrogen. So this one's going to be 3, and then the ethyl is actually going to be the lowest priority. Okay, so now what does the cross picture mean, the Fisher projection? The sides are coming out, yeep, and the top and the bottom are going away. What's in the plane? No bonds, okay? All right, so wow, I'm going to hold this like that. So I've got to have my purple and my green going away, and my red and my number 4 coming out. Agree? Okay, now which one do I grab? Number 4. So what do I have now? I have, here's my red, which is number 2. Here's my purple, which is number 1, and here's my green, which is number 3. So what are we doing? What? Okay, so it was like this. Green and purple are going back. Red and number 4 are coming out. Okay, I'm grabbing number 4. I'm pulling it away from me. And then I look at these. 1, 2, 3. What direction am I going? Counterclockwise. So which one is it? S. All right, what is still the hard part? How are we doing on the priorities? Okay, okay, then the hard part is moving it. You got to remember when you're moving this to the back that it's all connected. Okay, you can't just go 1, 2, 3. Okay, so when you pull this to the back, notice what happens to the red one. It pops to the other side. Okay, so start practicing that more. Do the homework. Do the homework in the book. Get yourself some practice. You come to the office and I'll watch you rotate if you want me to. And see if you're doing it right. It does not matter how you rotate because the molecule, all of them are still connected. So notice it's still S. Okay. Counterclockwise. Okay, allenes contain 2 carbon-carbon double bonds and share an atom. Allene is the name of the simplest one where there's all hydrogens. Okay, so look at this one. That would be this one. Okay, except that it doesn't matter what colors I used really. Okay, so here is H and Br, and over here is a fluorine and a chlorine. Notice that, look at that. They're not in the same plane, they're in opposite planes. Because the carbon in the middle here, what hybridization is that? Is it sp2? It's sp. There's going to be 1 p orbital going this way, and there's going to be the other p orbital going perpendicular to that. Okay, so that changes where these atoms are located. See how the double bonds are like this? Okay, because one's going this way and one's going this way. Okay, so what we have is, look at that. Is there a chiral carbon in here? Is there a carbon that has 4 different groups attached to it? There isn't, is there? But look what happens when we have a mirror image. Is it superimposable? See that it's not superimposable. Okay, okay, we'll flip these. All right, so I flip these so these match up, and look what happens down here, they don't match up. So allenes are an example of a molecule that can show optical activity, okay, even though there isn't a chiral carbon. So you have to be careful, you just have to look. What if I put a 3rd double bond in a row? What do you think? If I made 2 of the carbons in a row, sp hybridized. So I'm going to put another one in here. And yeah, people have run around trying to make these things. Okay. And they've shown that they are optically active. Okay, but what if I do 3 in a row? You see how it changed it? Now, do I have a plane of symmetry? I can cut right through all those atoms. Did you get that? Okay, we cut right through all those atoms, and notice that there's a plane of symmetry in here. Okay, if I have the mirror image of this, it will be superimposable. That's with 3. What if I put a 4th one? I'm going to flip back, right? Okay, so if it's an even number of double bonds, then it can have optical activity. Okay, and these don't have to be halogens. That just was the simplest, but you could have R groups on them. Okay, just like the other things. Okay, so in order to be optically active, remember to look for no plane of symmetry. No plane of symmetry. And you can cut atoms to make your plane. Okay? Okay, so find the chiral centers. Okay, so there's a little compound up there. Okay, how many chiral centers did you find? 1, 2, buckle my shoe, 3, 4. How many? 2. Okay, where are they? The one with the bromine is chiral, and the one with the OH is chiral. Everybody agree? Okay, now how many stereoisomers are there going to be? How many? So this carbon can be RRS, and this carbon can be RRS, basically. Okay, so there is a lovely little rule of thumb for you. 2 to the n. 2 to the n is the maximum number of stereoisomers, where n is the number of chiral centers. Okay, so 2 to the n, 2 squared is 4. Let's not all jump on those easy questions. Okay, so we're going to have so we're going to draw the stereoisomers as Fisher projections. Okay, so remember what a Fisher projection is? This thing, right? What we just had in that other problem. Okay, okay, so what we're going to do is we're going to use the cross part for where the chiral centers are. We're not going to use it for every carbon, only the ones that are chiral. Okay, so that would be these 2. See there? Okay, now typically what we do is we put the carbon chain down the center. It's not like it's a requirement, but it's something you're going to see, and you'll get used to seeing it that way because you're going to use these in other classes. So up here, I'm going to write CH2, CH3. That's these 2 carbons. Okay, and then I have my carbon that has what's on the chiral carbon? This one right here. A bromine and a hydrogen. What's on the next one? An OH and a hydrogen. And what's down here? CH3. Okay, so remember what a Fisher projection means. The sides are coming out. Okay, so here is not the one that I drew. So let me make it the one that I drew so it matches. Okay, here it is. So we have the H and the bromine coming out, and down here we have the H and the OH coming out. The top and the bottom are going backwards. Is this the most stable form of this molecule? No, because everything is what? Eclipsed, right? Remember that chapter? Wasn't that long ago. Okay, they're all eclipsed. Is this the most stable? No, but it is a convenient way to draw it. If you wanted to find the most stable, you would have to rotate, right? Okay, here we go. That's the most stable form of that molecule. Okay, so when we draw Fisher projections, we're drawing it conveniently because it's easier to see what we're doing. That's why we do it that way. Okay, so I drew 1, and now we're going to draw, we got to draw 4 total. Okay, so the best way to do it, my advice is draw 1, draw the mirror image. Notice the bromine and the OH are on the same side of the molecule right now, right? So I'm going to draw the mirror image. Where did my, here it is. Okay, so I'm going to go like this. Up here. Down here. Okay, what do I put over here? Okay, so there's two. Okay, there's two of them. Okay, now how do I draw the other two? We've only got two left. So since I had them both on the same side, what do you think I should do now? Flip them. Doesn't matter which one you flip. So let's flip the top one, just because. Now they're on opposite sides of the molecule, okay? Yes, you can rotate around that bond, but when you rotate around that bond, you don't end up with this one, okay? Because each one of those are chiral centers. Okay, so you draw one, draw its mirror image. Draw the other one and draw its mirror image. Okay, so it's going to look like this. Okay, so how many did we draw? 4. Don't draw more than 4. If you start drawing more than 4, you're going to be repeating these. So that's why being very systematic, just like we were when we did conformational isomers, really helps. I'm going to put them both on the same side, then I'm going to put them on the other sides. Okay, then you get all 4. Okay? All right, now, what is the relationship between A and B? Enantiomers. Enantiomers are non-superimposable mirror images. Do you agree that those are non-superimposable? You think about picking that up and turning it around and trying to, they ain't going to match up. Okay? Because you're going to have an ethyl and a methyl. Okay? So enantiomers would be A and B. Is that the only pair of enantiomers up there? What about these two? C and D. Are they enantiomers? Are they non-superimposable mirror images? Are they mirror images? Yes. Are they non-superimposable? Yes, they are enantiomers. So this is also a pair of enantiomers. This compound has 2 of those. Okay, now what is A to C? Look at A and look at C. They're both stereoisomers, right? We still have, if you count from the top, the bromine's on carbon 3, the OH is on carbon 4, and then you have the methyl. It's still hooked together almost the same, except for 3D. But are A and C enantiomers? No, because they're not mirror images, right? They are a new thing. They are called diastereomers. Okay? Diastereomers are stereoisomers that are not enantiomers. You cannot have diastereomers until you get to 2 or more chiral centers. Okay? So when we had only 1 chiral center, all you can have are enantiomers. You can't have a diastereomer. Okay, so what are the pairs of diastereomers that are on this slide? I already told you one. That was A and C. Okay, who else are diastereomers? B and D. Okay, there's more. A and D. And there's one more. C and B. I'll write it B and C to make it match. Okay. Doesn't matter though. All right, does that make sense? Okay, some things about diastereomers. You should have a slide of diastereomers. Diastereomers are stereoisomers that are not an enantiomer. typically will have 2 or more chiral centers. Remember, I showed you the allenes. They kind of screwed it up a little. Okay, diastereomers have different physical properties. So you could separate them in the lab. Now, does that mean it's easy? Well, easy is a relative term. It's a whole lot cheaper, though, than trying to separate enantiomers. Enantiomers are much harder to separate. But physical things are going to be different. They're going to have different boiling points. So you could do fancy fractional distillation. There may be soluble slightly different in a solvent, and you could get one to recrystallize out and the other one to stay in the solvent. Okay, there's little tricks like that that can be employed. So they have different physical properties, whereas enantiomers have all the same physical properties. Okay. Okay, so here's all of our isomers. This might be at the end or of your deal because I moved it. I know I moved it. Okay, here are constitutional isomers. Those are structural isomers. They're hooked together differently. Same formula, different structure. Okay, stereoisomers, okay, are a little bit different. They are hooked together really the same, yet they're not the same, okay, because they are mirror images and stuff. All right, so enantiomers and diastereomers are under stereoisomers. There are 2 categories under stereoisomers, okay? Enantiomers are non-superimposable mirror images. Diastereomers are not. But they still have, like on carbon 2, we had an OH, and carbon 3, we had the Br. They're still hooked together almost the same, okay? These are 2 or more chirality centers. And then, do you remember these guys? Cis and trans with double bonds, okay? Those are a form of diastereomers. Okay, they only differ in 3D. They still have a carbon with an H and an R on each one, and the R can be a halogen or some other element. Okay, everybody see how it all kind of fits together? Sometimes that helps to remember them. Okay, what if I say, tell me if it is R or if it is S? Okay, how do you do that when you have more than one chiral center? Well, typically do each chiral center, just do one at a time. Okay, so like if you start here, tell me, is that carbon R or S? Okay, so what do? Do all the priorities. Yeah, start with your priorities. Okay, so who's 1? Bromine is going to be 1. Who's 2? The carbon down below. Who's 3? The ethyl. Okay, and so poor little hydrogen is 4. Okay, so when you do this, what's coming out? The bromine, which I made purple, and the hydrogen are coming out. And then here's the green and the red. Okay, see how I got that? Now I grab which one? 4, the hydrogen. Okay, and I'm going to pull it back. Okay, you do it first, and then I'll do it. See if you can figure out what it is. Do you think it's R or S? Technically, you have a 50-50. You would like to get those 50-50s right. Okay, so I'm going to grab this and I'm going to pull it back. And what is going to happen to the purple one? It's going to pop over here, right? Okay, so now I will have, I've got the purple. So much for changing colors. Okay, there's 1. Here's 2. And here is 3. What do we get? What? Well, if you're going clockwise, it's R.
So I have a dumb question, and I know that there's going to be something that's going to prove me wrong.
Uh-huh.
But when they're all written out, it seems like the ones that are S, when they're written out like that, they're always going to be R when you flip it. Like, so
It has to do with where it's oriented. If this was 4, it would be going back already.
Okay.
So then things don't flip so much. When it depends on where they're oriented. Yeah. Mhm. All right, so let's do the bottom one. Okay, so we're going to do the bottom carbon. So that's this one, the one that now has purple on it. Okay, so who's number 1? Bromine. Who's number 2? The top stuff. Who's number 3? The ethyl. And who's number 4? Hydrogen. Okay, so I want to have this so that I'm holding it in that same orientation. So I want the H on the right and the bromine, which is the purple one, to be going out. So see, I'm holding it like this. I got it wrong. Maybe today. Okay. I think I just glanced at the top one when I was looking at the colors. Okay. All right, let's try again. Okay, so here's hydrogen and bromine are coming out. Here's the red at the top. Here's the green at the bottom. I'm going to grab number. I'm going to pull it back. Okay, so what do we have now? We have the purple. That's 1. The red, that's 2, and the green, that's 3. What do we get? We got our. Okay, is that what you got? No? Okay, so to write it in the name, okay, when you write out the whole name of the thing now, you have to be careful and look and see, is it a chiral center? What is the configuration of the chiral centers? Okay, so we're going to have 3R, 4R, 3,4 dibromohexane.
Why is 3R and 4R?
1, 2, 3, 4, 5, 6. Okay? Don't forget all the rules of nomenclature. They're all still there. Number 1, find the longest chain. Number 2, okay? All the rules are still there. All we're doing is adding this. 3R, 4R. See, you could have 3R, 4S, right? Okay. You could have 3S, 4S. Get the idea? You can have all these possibilities, and that's how come they have to be designated by a letter. If there's only one chiral center in a molecule, all you do is put RS in front of the molecule. Okay? Okie dokie. Okay. All right, so what? You want me to go back? Okay. This thing went away because it resets when you go back. See, now it's being a butthead. I doesn't want to. Okay. Okay. All right. So, have you heard of D and L? Capital D and capital L. Not to be confused with little d and little l. What's little d? No. Dextrorotatory. And what's little l? Levorotatory. Okay, what does that mean? What does dextrorotatory mean? Rotates plane polarized light clockwise to the right, and levorotatory is to the left, counterclockwise. Oh my gosh. Okay, I told you there's a lot of new words in this chapter, and we're not done yet. Okay, so the DL system uses capital letters. So it's going to be important that you write capital letters versus little letters, okay? It's used for carbohydrates and amino acids. Typically, those are the only things. It's an old system that has been around for a long time, okay? So what are D and L, and how do they relate to R and S? Okay, so this is a compound. Have you ever seen that? What does CHO mean? You remember what CHO means? That aldehyde thing. Okay, this is a compound called glyceraldehyde. Have you heard of that? It is the simplest, smallest carbohydrate. It has 3 carbons in it. It has 3 carbons in it. Okay. This one is D-glyceraldehyde. Why is it D? Because somebody decided it was D. It's truly what it was at the end. Well, when I show you a bigger carbohydrate, I'll tell you that other thing. All right, so this is going to be L-glyceraldehyde. Okay, so they put a capital D in front and a capital L in front. Typically, their font size will be a little smaller. Like I wrote it, you'll see it that way when you look stuff up. Okay. All right, now, is D-glyceraldehyde R or S? You already figured it out? Yeah. Okay, what do you think? Okay, you got your priorities? Who's 1? OH, who's 2? CHO, who's 3? The thing on the bottom, who's 4? Hydrogen. I'm going to pull the hydrogen back. Remember what it means. Those 2 are coming out. Top and bottom are going back. I'm going to pull the hydrogen back, and what happens to the OH? Flips over to the other side. So it's going to be 1, 2, 3. So this one is going to be R. You don't get it? Sit down and try to work it through. Okay? Because it's a different system. You'll notice we didn't put plus and minus in here either. Sometimes that isn't used. D and L is an old system that was used many moons ago. Okay, and you'll see why they still use it, at least in carbohydrates. S is the S, this is the S one. You figured out one, you figured out the mirror image, right? You just got to figure out that one right. It's only key. Okay, so that's our glyceraldehyde. Okay, now when you look at a carbohydrate like this, and we know what that is. It's glucose. How many chiral centers are there? Holy crap. There's how many? There are 4. And because of that, there are a whole bunch of stereoisomers of glucose. Have you heard of mannose? Have you heard of all those little sugars? Yeah, you'll have the joy of learning them one day, if you haven't had that joy yet, of learning all their structures. You'll notice that every time we draw them, and they have 2 forms. They have a straight chain form, and they have a ring form. I don't want to spoil all the fun for Dr. Pryba, but when they make the ring form, oh my gosh, then we get another chiral center. Okay, so there's a whole lot of chiral centers. And since they didn't want to have to designate 2R, 3R, 4S, 5S, whatever it is, okay? They didn't want to do that. So what they said is, we're just going to figure out what this one is. Okay? So notice that the CHO is at the top, the CH2OH is at the bottom, the OH is on the right, and the H is on the left. Okay, which glyceraldehyde did that look like? The D one. So look back at the other slide. It's easier for you to do it than me, actually. And because the OH is on the right, it's D-glucose. So no matter where the other ones are, it's kind of irrelevant. That gives them their actual name. Whether the bottom one is on the right or the left tells you if it's D or L. Okay? when they were working with carbohydrates, woohoo, back in the dark ages, they would actually try to figure out the structures by breaking them down. And then they would take the very last carbon after they busted the molecule up, and they would take that compound that was formed and they would decide, is that D-glyceraldehyde or is that L? And that's how they decided the whole thing was D or L, was by that very last one. They compared it. And that's how come the D and the L got started. Okay? All right, so I'll look at this one. Oh, I actually put the D-glyceraldehyde up here for you. I forgot I'd done that. All right, so here's the amino acid. Amino acids have an amine and a carboxylic acid piece. Okay, and then this carbon right here is your chiral center. Okay. Okay, this one happens to be called alanine. I'm not going to make you learn them. All I want you to be able to do is tell me if it's D or L. Okay, so we're going to look at this. This is going to equate, I have to go back to the arrow to get that to go away, is going to equate to this, the CHO. And the NH2 here is going to equate to the OH. And then, of course, you got an H and an H. That was kind of nice. One thing actually matched. And then down here, you have whatever your R group is going to be for your amino acid. And here is the CH2OH. So since the H's are both on the right and the NH2 is on the left, it has to be in this orientation to decide if it's D or L. Well, this over here is L-glyceraldehyde, so this is L-alanine. Is that R or S? Okay, well, you have to do your priorities. So who's number one? This one is. Who's number two? That one. Who's three? This one. You pull the H back, and what do you get? S. Okay, but they don't use, if you actually went to buy alanine because you needed it for something in the lab, you're going to feed one of the enantiomers through bacteria and see what they did with it or something. Then sometimes you can find it under R or S when you order it, but typically it's going to be under D or L. Okay, D or L. We use nearly all L amino acids and all D sugars. Okay, bacteria use the opposite. Okay, they use L sugars and D amino acids. So if we can inhibit their synthesis that they do using those, they won't hurt us, but it'll hurt them. Okay, and that's how we kill them. All right, so you got D and L. It's kind of weird. It's a weird old system. That is, and that's all it really gets used for. So don't panic about it, even Samuel Jackson. Okay, now there's some other old terms that are still used a lot. They are erythro and threo. Erythro is also based on looking at those Fisher projections. Remember to draw your carbon chain down the middle. Okay, that makes all the difference. And then you're going to look at the groups. Okay, if they're on the same side, they're erythro. If they're on opposite sides, it's threo. Okay, so didn't we have I guess we'll just do this. Okay, didn't we have something like this? Well, I'll just draw something. It doesn't have to be the same thing that we drew. Okay, so look at that compound and tell me, is that erythro or threo? It's erythro, because the two bromines are on the same side. They have to be drawn in that orientation. You can't swap the bromine and the ethyl, for example, okay? It's the only way this little thing works, okay? ESTO, that's how I remembered it. I always had trouble. I wanted erythro to be opposite because they were vowels. It doesn't work. So you got to go ESTO, ESTO to get it in your brain.
So whenever we're looking at glucose earlier, how would you break that down?
Okay, so what they would do is they would say, let me make it skinnier. Hang on. Okay, they would write erythro hyphen, and then they would go 2,3 dibromo. Do I have 5 pentane? And that, or they would talk about it and they would refer to the erythroisomer. Okay? If they were talking about the stereoisomer, draw me one of those. So 3O means they're on opposite sides. So I've got my carbon chain going down the center. So now for it to be 3O, I have to have a bromine on one side and a bromine on the other side. There's going to be 2 erythro and 2 3O, right? Because you'll have the mirror images. Okay, so this is the 3O one. ESTO. Esto. Can't think of anything else. That was the only way I finally got it. Okay?
Is it the same as this?
No, because you can rotate around this bond. Okay? Yeah, it's just a designation like DNL, really. Okay? So this compound here, I'm going to show you some compounds and you can tell me. Is that erythro or is that 3O? It's what? Erythro, because the 2 OHs are on the same side of the molecule, okay? This compound is called erythrose, and it is D-erythrose. That's how it got its name, because the OHs are on the same side. And it's D because if you look at this carbon right there, the OH is on the right, so it's D-erythrose. Okay, so look at this compound. What is that one? Erythro or 3O? 3O. Okay, so guess what this one is? This is 3Os. Is it D or L? L. You got it. Okay, so up here I have the other ones. This is also erythro, but that's L-erythrose. I mean, they all exist whether we use them all or not. Okay, they all exist. Okay, and then down here, this one is 3O, and that's D3Os. Okay, is that the D and the L is decided by the bottom chiral carbon. They have to be drawn in that way, where you have the aldehyde at the top and the CH2OH on the bottom. Okay? You got it? Okay, so if you had to memorize, let's see if I can, the ones that usually you have to usually memorize all of them. And you start with the glyceraldehyde, and then you add another carbon. You get the erythros and the 3Os. Then you add another carbon. You get the 5 ones. The hardest ones to memorize are the 6s. And if I will show you how I memorized them. Okay, so this is going to be for glucose. So I know, and I got where I wouldn't even write all the stuff in. All I would do is go right, left, right, right. And that's where the OHs are. So if you have to memorize them, you're going to go like that. And you're going to go right, 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 right. That's another one. Okay, I don't remember them all anymore. Isn't that terrible? Left, left, right, right. It's all the possibilities. So just learn the possibilities, okay? When you have to memorize them, you'll have to memorize them in biochem maybe, cell and moleculite, metabolism, biochem 2, you might have to memorize them. So just learn where the OHs are, and you'll learn everything else because it's the same every single time. And then you can, we would sit down with a piece of paper and do this and write them all out so that we had them all in front of us when we would take a test and we had to learn them all. So does that make sense? That the lines are the OHs. Okay, so Wednesday is Halloween.
What'd you say?